Hello students, in metric space we have studied compact, sequentially compact, countably compact, Bolzano-Weierstrass property. Bolzano-Weierstrass property. In metric space, compact, sequentially compact, countably compact, Bolzano-Weierstrass all are equivalent. But in topology, they are not equivalent. Compactness implies countably compact, sequentially compact gives countably compact, and countably compact gives Bolzano-Weierstrass property. Now, every metric space is a topological space, but a topological space need not be a metric space. Now, for this we see, let Xt be a trivial topology defined on a non-empty set having two elements, having at least two elements. Extreme topology means in discrete topology, the topology having only two elements. Then it is not a metrizable space. It is not a metrizable space. Now, what do you mean by metrizable space? Activate in discrete topology, define a non-empty set having two elements, then it is not a metrizable space. Because we know that every metric space is a topological space, but a topological space need not be a metric space. Now we will prove, we will show it by an example. Now first we come to metrizable space. A topological space Xt is a metrizable space if there exists a metric D on X such that there is a metric D on X such that topology induced by D is same as Xt. A topological space Xt is a metrizable space if there exists a metric D on X such that open set induced by this D and this topology, they both are open set are same. That metric is said to be metrizable space. Now there is a difference between a metric space and metrizable space. Metric space and metrizable space. Metric space is a metric defined on a set. Metrizable space is a topological space whose topology is induced by metric D defined on X. That is known as metrizable space. Now we will show that from a topological space need not be a metrizable space. Let X be a set having two elements and T be a topology induced trivial topology, or you can say in discrete topology. Let and we saw it is not meterizable. The open set, if you define a metric on it, the open set of metric space and this topology are not same. Let A and B be two distinct elements. Let D, the distance between these are opposing to is greater than 0. Now from here we say that A belongs to a sphere with center A and radius R, and this is not empty, and this sphere A belong to that, it is not equal to also X, and in discrete topology we have only two open set phi and X, and here we have open set a sphere with center A, radius R, the element A belong to this is not an empty, and this is not equal to X. So the open set induced from here and the open set here are not both same, hence from here we conclude that a topological space need not be a metric space, but every metric space is a topological space. Now we come to next. Every compact space is countably compact. Now before that, we recall the definition. What do you mean by compact space? What do you mean by sequentially compact? What do you mean by countably compact? What do you mean by Bolzanus-Listus property? Bolzanus-Listus property. Compact space. A topological space is said to be compact space if every open cover has a finite subcover. A topological space is said to be sequentially compact if every sequence has a convergent subsequence. Countably compact. A topological space is said to be countably compact if every countable open cover has a finite subcover. Bolzanus-Listus property. A topological space has a Bolzanus-Listus property if and only if a topological space is said to have Bolzanus-Listus property if every infinite subset A of X has element point, or you can say every infinite subset of X has element point. Bolzanus-Listus property. Now we come to every compact space is countably compact. Proof. Compact means every open cover has a finite subcover. Countably compact means every countable open cover has a finite subcover. Let Xt be a compact space. Xt be a compact space. Let C G and N belong to N be a cover of X. That is, X can be written as union N belong to N G N. Let X be a compact space. Let be a countable cover. In fact, be countable. Be a countable cover of X. Be a countable open cover of X. Countable open cover. X be a topological space. C be countable open cover of X. But X is given to be compact. But X is compact. So X has a finite subcover. A topological is said to be compact if every open cover has a finite subcover. X is compact, so it has a finite subcover. So it has a finite subcover. That is, you can write X is equal to union I1 to N Gi. Okay. Now, what is the definition of countable compact? A topological space is said to be countable compact if every countable open cover has a finite subcover. Now here, this is countable cover and this is a finite subcover. From the countable cover, we find a finite subcover. Every countable open cover is a finite subcover. Then the topological space is said to be countable. How you conclude that every countable open cover has a finite subcover, hence every compact space is countably compact. Now we move to next. We have shown every compact is countably compact. Now we will show every sequentially compact is countably compact space. Proof. Sequentially compact. A topological space is said to be sequentially compact if every square has a convergent subsequence. A topological space is said to be countably compact if every open countable cover has a finite subcover. Let Xt be a sequentially compact space. A sequentially compact space. Case first, if X is finite, then it is obviously countable compact because it is a finite open cover, so it is X is finite, so it is obvious countably compact. Second case, if X is not finite, set assume that X is not countable compact. If it is not countable compact, there is a countable open cover of X which has not finite subcover. Okay, because it is not countable compact, so there exists a countable open cover which has not finite subcover. Let C G N belong to N be a countable open cover of X, and it is not countably compact, so it cannot reduce to a finite subcover, the countable open cover, but X is not countably compact, so there does not exist a finite subcover of X. That is, X cannot be written as union I1 to N Gi. X cannot be written as. Here X can be written as, it is cover of X. X can be written as union and belong to N Gn. If X is finite, then it is already countable. If X is not finite, set we assume X is not countable. We assume first X is finite. Okay, if X is not finite, set And we further assumed, we've already taken which is sequentially compact. We assume that X is not countably compact. If it's not countably compact, is a countable open cover, and if it is countable open cover, then it can be written as this. But X is not countably compact, so does not exist a finite subcover of X that can be written in this way, that is X cannot be equal to that. Now let M1 be a least positive integer such that M1 be the least positive integer such that X intersection GM1 is non-empty. Okay, if it is like that, this is GM1 and that is X. This intersection, this part, it is non-empty, so we can choose an element, say x1 from this intersection. Let x1 belong to X intersection GM1. Again, let M2 be the least positive integer such that M2 greater than M1 and X intersection GM2 is non-empty. Now we choose an element x2. How we choose? This is X, this is GM1 and this is GM. Now we choose X intersection GM2 is non-empty. Now choose an element x2 such that x2 belong to X intersection GM2 minus GM1. That element is come from this region, only this, which excludes GM1. Open set it excludes. This implies x2 belongs to X intersection GM2 and x2 does not belong to GM1. Continuing in this way, we choose continuing in this way. We have chosen x1, we have chosen x2. Now we again will choose x3. Continue this way. We have a positive integer m3 such that m3 greater than m2 greater than m1. It is the least positive integer. How we construct? X intersection GM3 is non-empty. How we choose element? We will choose like this. This is X, this is GM1, GM2, this is GM1, this is GM2, this is GM3, this is GM3, this is GM2 and this is GM1. Now we choose the element from here in this region. X3 belongs to X intersection GM3 माइनस में GM2 माइनस में GM1. That is, this implies X3 belongs to X intersection GM3 and X3 does not belong to union I 1 2 2 X intersection GMI. X intersection MI. We choose the element in this way. Now we continue this process. On continuing this process, we choose ith element. Xi belongs to X intersection GMI and Xi does not belongs to union J12 I minus 1 X intersection GMI. Okay, we will choose this way. In this way, we obtain a sequence, say Xn. We have constructed a sequence. The process of construction you see in this, but Xt is countably compact. But Xt is sequentially compact. But Xt is sequentially compact. You have taken sequentially compact. So it has a convergent subsequence that converges. Let limit n tend to infinity X n I tends to X. It is a convergent subsequence. Now X is equal to union n belong to n, and this point belongs to X. Here X is equal to this. This implies X belongs to union n belong to n Gn. This implies X belongs to Gp for some P belongs to n. Now X belongs to Gp for some P belongs to n. Since X intersection Gp is non-empty, therefore there exists a Q, there exists some Q, there exists some Q belong to n such that Gp is equal to Gmq. Now for I greater than Q, Xi does not belong to Gmq. By construction of sequence, but X belong to Gmq. The sequence converges to this element X. If a sequence converges to this element X and that belong to this, so all the terms of the sequence must lie in it, but they do not lie in this. So it is a contradiction to the fact that every sequence has a convergent subsequence. So our assumption is wrong, that it is not countably compact. Hence, it is every sequentially compact is countably compact from this. Because if you converge it, all the elements of the sequence lie in this neighborhood, but by construction they do not lie in this. So it is not simply compact, but we have given sequentially compact. Hence our assumption that it is not countably compact is wrong. Hence every sequentially compact topological space is countably compact.